So we have a function here and we have the tangent line. The tangent line at this red point, and I want you to watch what happens as I move the point. First, I'm just going to move the point along the whole function, and then I'm going to do it again and point out the things that I want you to pay attention to. But notice as it moves, it's always tangent to the function at this red point that I'm holding. So the line is changing, of course, but it is always touching the function. Now we're going to do that again, and as we do it the second time, I want you to track the line as it rotates. It's also going to be moving along the function, but I don't want you to pay attention to the movement, only to the slope of the line as it changes. So here we start with a slope that is negative and quite big. The line is almost vertical. Watch what happens now. It's not surprising that at the minimum point the line is horizontal, slope 0. Now it has a positive slope. Right around here it looks as if this is the biggest slope that it's going to have, because now the slope is going to 0 again at the maximum point, and it continues to be negative. So as I was moving the line the second time, I was pointing out when it's positive and when it's negative, because those are the things that you're already used to looking at. But the next time, I don't want you to look at the line at each specific moment and consider whether it is positive or negative slope. Instead, I want you to look at the motion as a whole and think about whether the slope is getting bigger or getting smaller. So we're not going to look at photographs of the function with a specific tangent line right now. We are actually looking at a video. The slope starts here very negative, but now it is increasing. It's not so negative anymore. It continues to increase as it gets to 0, as it gets past 0, and now it's decreasing again. It's still positive, but it's decreasing, reaches 0, continues to decrease as it becomes more and more negative. The reason why we're looking at this is that the slope of the tangent line is the derivative of the function, which you can also think of as the rate of change of the function. So the slope of the tangent line is how fast the function is increasing at that point. And we can see that here it is not increasing as fast as it is here, for example. So the derivative is always the rate of change of something. And until now, you've been looking at the rate of change of the value of the function. It's changing. The value of the function is the vertical coordinate of the points here, right? So the value of the function is changing fast. The value of the function is changing slowly. But the thing that we are looking at is the rate of change of the value of the function. Now I want to look at the rate of change of something else. I want to look at the rate of change of the slope of the tangent line. That's why I told you to keep track of the rotation of the line as it moves along the function, because here we have a slope that is increasing. It has a positive rate of change. And when it's rotating this way, we have a slope that is decreasing. It has a negative rate of change. This can be confusing to look at in the beginning because you get the photograph mixed up with the video. So if you're looking at this, for example, you're seeing a positive slope. You're seeing a line that is going up. But you're thinking of this positive is the rate of change of the value of the function here. And that's not what I want you to look at. I want you to look at the video, and the thing that is decreasing here, the negative rate of change, is the slope. You can't see it if I stop my hand and say, look at this. You can only see it if I'm moving. This is a negative rate of change for the slope, and this is a positive rate of change for the slope. It doesn't matter if I'm at this part of the movement or at this part of the movement. The line is decreasing here and the line is increasing here, but all throughout this motion, the rate of change of the slope is positive because the slope is getting bigger. The line is rotating this way. So let's look at that again in the function. Here we have a positive rate of change for the slope. And here we have a negative rate of change for the slope. And the point here is that after you do this a few times, you start to see this distinction on the function itself. You don't have to be keeping track of a tangent line. We're only doing this until you understand what to look for on the function itself. The part where the rate of change of the slope is increasing is this part here, until here, right? So this part, it is where the function looks like this. It is facing up. But here on the other side, when the slope of the tangent line is decreasing, see which way it's rotating? The slope of the tangent line is decreasing here. The function looks like this. It looks like something that is facing down. You already know this word. We are talking about concavity. You've heard about this before because you've studied quadratic functions. We have concavity up and we have concavity down. But the thing is that a quadratic function can only have one of those. It is either facing up or facing down. And in calculus, we like to study all functions. The functions have the freedom to do whatever they like. So most functions look like what we're looking at right now. They are concave up in some parts and concave down in other parts. Just like lines are either increasing or decreasing, but functions in general are increasing in some intervals and decreasing in some other intervals, right? So concavity is the same. Quadratic functions only have one of those. They're either positive or negative, but functions in general have intervals where the concavity is up and intervals where the concavity is down. We already know that the derivative of the function is going to tell us how to distinguish what is increasing and what is decreasing, because that is the rate of change of the function. If the function is decreasing, it has a negative rate of change, therefore a negative derivative. And today we want to learn how to distinguish the concavity down from the concavity up. And this is about the rate of change of the slope. So here we have a line that is rotating this way. The slope is decreasing. That is concavity down. And here we have a line with slope that is increasing, rotating this way. That's concavity up. The rate of change of the slope of the tangent line tells us the concavity. But the rate of change of something is always a derivative. That's what derivative is. It's a rate of change. So we're looking at the rate of change of the slope, but the slope itself was already a derivative. The derivative of the function is the slope of the tangent line. And the rate of change of that slope is the rate of change of the derivative of the function, which is the derivative of the function. So we're taking two derivatives. This is the second derivative of the function, which is telling us about the concavity. When the second derivative is positive, the concavity is up. And when the second derivative is negative, the concavity is down. If you're feeling uncomfortable defining concavity up as something that looks like this, that's an interesting feeling because this definition is strange. So let me give you another one. Notice how in all of the parts where the function has concavity up, the tangent line stays below the function. It can be a decreasing line or an increasing line. But either way, the line is under the function. And in the intervals where the function has concavity down, it is the opposite. The tangent line is above the function. All through this interval here, the tangent line is above the function. So that's interesting as a definition of concavity. You don't have to think of it this way. It's totally fine to think it's just something that looks like this or like this. But it's good to look at it at least once because we have to realize that if in this interval the tangent line is above the function and over there it's going to be under the function, then at some point it's going to have to switch sides. Let's see if we can find that point by keeping track of whether our line is above the function or under the function. Now the bottom part of my line already looks like it's under the function, right? This thing that I'm using as a tangent line is not long enough, but the tangent line itself is infinite. So you have to see that at some point around here, the bottom part of the tangent line is under the function, while at the same time, the top part of the tangent line is above the function. And this is necessary. This has to happen because otherwise we can't change from concavity up to concavity down. There has to be a point somewhere where the tangent line is crossing the function from the top to the bottom. The same line at the same point It is still a tangent line. That's why I built this way, where the tangent line is stuck to the function. But sometimes it's under the function and sometimes it's above. So there is a point somewhere where the tangent line itself is crossing the function. And that's why you can't really define a tangent line as something that touch but doesn't cross, right? I know that in the very beginning we feel like doing that because most tangent lines are like that. They touch but they don't cross. I know that at some point I must have told you that this is a bad definition for other reasons. For example, this tangent line here is touching the function. It is a tangent line, but it is an infinite line. So if you extend it, it is going to cross the function over there. So the definition touches but doesn't cross has other issues. But that one we could put down to, oh, but this is a local concept. We shouldn't be looking at something that happens elsewhere. This point is different. At this point, the tangent line is crossing the function right at this point, right at the point where it's tangent. This is an actual issue with that sentence as a definition. We shouldn't say that a tangent line is something that touches but doesn't cross. And that is an issue that the official definition of derivative doesn't have, right? This definition is purely a calculation. It's not judging whether crossings are happening or not. It's not judging anything. So that's why this is the official definition, because it works for all the points. But the thing is that the official definition has all of these advantages once you've already understood the concept that we're talking about. If you only look at it and you've never thought about any of these issues before, this definition is not going to really help you to understand what a tangent line is, which is why I always like to skip that part, postpone it for later, because the definition of the tangent line is this. I'm not even going to say that it's a line that doesn't cross. I avoid saying that sentence, but I just say, look, a tangent line is a line that looks like this. It sounds horrible as a mathematical definition, but I'm not trying to be mathematical. I am trying to be intuitive. And when you think about solid objects, this is super intuitive. When if you touch a line to this thing, what's it going to look like? Here, it looks like a tangent line. This thing is not exactly very solid, so I'm having to try to intentionally make it tangent. But in order to first explain to a student what the concept of a tangent line is, that's it. It's a line that goes like this. Look, it's touching the solid object. And yes, there is a problem at this point, right? At the point where the concavity is changing from down to up or vice versa. But that is not the problem that comes up in lesson number 1 when we are explaining to the students what a tangent line is. This is a problem that comes up now when we start talking about concavity and the derivative of the derivative. So this, in my opinion, is the moment to show you the official definition. I don't like talking about limits early on in a calculus course. Limits are difficult. Derivatives are easy. Limits are boring. Derivatives are fun. And I do think that the students should see the fun, easy part first before they start handling the difficult, boring, technical parts like limits. So anyway, back to the video. This is what we want to do today. We want to explore further the relationship between the value of the function, the value of the derivative, which is the slope of the tangent line, and the value of the second derivative, which is the rate of change of the slope of the line itself. Let's get something out of the way first. Mechanically, in terms of what you are able to do with the functions, nothing changes today. You already know how to take one derivative. Then the only thing that's going to happen is that you are going to do it again. This one is the rate of change of that one, and this one is the rate of change of that one. So if you have this function and you want the slope of the tangent line at some point, then you use this one. But if you want the concavity at a certain point, then you just have to do a second derivative here. And it's the same derivative rules as always. If you have to use the chain rule, then you're going to use the chain rule. And if you have to use the product rule, then you're going to use the product rule. It's the same derivative rules, so it's not something new that you need to learn how to do. It's just how to interpret what it means in terms of the graphs of the functions. I am pretty sure you're already familiar with this, so the only thing that we're going to do is to extend it to the second derivative. So what is going on here? Whenever the function is increasing, the derivative is positive. When the function is decreasing, the derivative is negative. In between an increasing and a decreasing interval, you need to have a point of maximum, and that is where the derivative is 0. You can keep going with this just to illustrate the minimum point also has a derivative of 0. And there is nothing that the first derivative will do to distinguish this 0 from this 0, like to distinguish a maximum from a minimum in a function. But you already knew that. Every time that you take a function and you set the derivative equal to 0, you know that you're finding this point and also this point. But today we were talking about something slightly different from this. We were talking about when the derivative is increasing. That's when the tangent line was rotating this way. So we already know that whenever a function increases, its derivative is positive. So that's going to happen here as well. This function is increasing and its derivative is going to have to be positive. And in fact, this whole block here is going to be repeated here because this line is the derivative of this line, just like this line is the derivative of that line. It's the same thing, only we're now looking at this function instead of looking at that one. But now we can say more because we spent a few minutes looking at what happens when the derivative is increasing, which is when the tangent line is rotating this way. That is a point where the function has concavity up. So we're going to put that concavity up right here. Same goes here because that is the same. And over here where the derivative is decreasing, it's when the tangent line was rotating the other way. So that is concavity down. In between the two types of concavity are those strange points that we were talking about, where the tangent line crosses the function and moves over to the other type of concavity. So a point around here that looks kind of like this with a tangent line crossing the function. And the name of that type of point is inflection point. An inflection point is where the sign of the concavity is changing. So the concavity is going from positive to negative at this point. That's where it's changing. So this is the inflection point. And so is this one. Because inflection points can happen with decreasing tangent lines like this one, but they can also happen with increasing tangent lines like this one. And they can also happen horizontally. If a function goes like this, it looks like it's about to go back up, but then it sort of changes its mind and goes back down. This point here is also an inflection point. It has a horizontal tangent line, but the concavity was up here and the concavity was down here on this side. I am just looking at what the function looks like to say these things, but if you want to imagine the tangent line rotating here, you can see that the slope is increasing, or you can just look at the fact that the tangent line was under the function at that part. And on the other side of the inflection point, now we have tangent lines above the function that rotate the other way as it moves to the right. So here's the thing, all of these are inflection points because the concavity is changing at all three of them. But this one also has a horizontal tangent, so it has something in common with the other blue points here, which is the horizontal tangent. But these two are called turning points. Those are the maximums and minimums, as you already know. They both have horizontal tangent line. But so does this one, and that one is not a turning point because a turning point is when the function changes direction, either from decreasing to increasing or from increasing to decreasing. And this point is not doing that. It is just decreasing. Function was going down and it keeps going down. But they do have something in common, all three of them, which is the horizontal tangent line. So that deserves a name. That's a stationary point, okay? The function is not going up or down at that point. It's just going horizontally because it has a horizontal tangent line. Some people also call these critical points. That's a synonym. It means exactly the same thing. But going back to the table that we were building here, there is something else that we can fill in, and that is going to be useful to distinguish the maximum from the minimum in terms of turning points. notice that the maximum of a function is always happening at an interval of concavity down. So over here, the maximum point, which is indistinguishable from the minimum because they both have zeros in the first derivative, but they're not so indistinguishable because in the second derivative, this one is going to have concavity down, so it has a negative second derivative, and the other one has a positive one. You can't really say anything here. I know it feels a little bit frustrating to have an empty space on your table, but the thing is that this function is decreasing here. So it is decreasing, and at some point it's going to have an inflection point to go from this concavity down to this concavity up, but we're just not seeing that in the table. We don't have a separate square for before that point, after that point, so we just leave it like that. Please do not memorize this table as a set of symbols. I do want you to be able to write this down again exactly like this from memory whenever you want, but not because you memorized it, but because you understand all of these concepts and how the things relate to each other and what are the important things to point out in the table, right? In fact, do that right now. I've taken it away from the screen, so pause the video, grab a piece of paper, and write down the table again. Okay, so now I want to look at how this can appear in exercises, in exam questions. And first of all, a lot of the time it is going to be about this distinction between the maximums and minimums of the function, okay? You're going to take one derivative, take two derivatives, and look at that point if it is negative or positive. And that's how you're going to distinguish if your point with slope 0 was a maximum or a minimum. That is a very common thing for them to check if you know. It is called the second derivative test. And here is an example. They're giving us a function. We're definitely going to want the first and second derivative of this function. So let's use the product rule here and then take the derivative of that. And now let's go see what the items are asking us to do. Find the value of the y-intercept. That's age of 0, which is 3. Find the first derivative. I've already done that. It is 2x e to the power of x plus 2e to the power of x. Hence, find the coordinates of A. A is the minimum point, so that's going to happen when this thing equals 0, which is when x is equal to -1. Now, instead of asking me to find the second derivative, he gave me a show that, because he doesn't want it in that format that I wrote up there. He wants me to factor out the e to the power of x. So it's going to look like 2x from here, 2 plus 2 is 4 from here, and then e to the power of x. Now notice that this question came with a graph, so he is not going to ask us to decide if the point A was a minimum or a maximum, because I can see that it's a minimum. But if the question didn't come with the graph, then he wouldn't be referring to it as point A. He would say find the coordinates of the turning point. Oh, and by the way, I forgot to do that question, right? Because it was coordinates plural, so he wants f of -1 as well. And then after asking for the second derivative, or even without asking for the second derivative, he would say decide if this point is a maximum or a minimum. And then what you would do for that question is that you would take the second derivative and you would calculate that at that point, -1. So it's going to be -2 plus 4 e to the -1, which is equal to 2 over e. That is a positive number. So we are talking about positive concavity at a point where the tangent line is horizontal. That is a minimum. That is a very common way to test for second derivative in exam questions. This question didn't exactly do that. He said find the values of x for which the graph is concave up. So concave up is when the second derivative is bigger than 0. So you're going to need the 2x plus 4 to be bigger than 0, right? Because the e to the power of x is always bigger than 0. 2x is bigger than -4, and x is bigger than -2. That matches nicely with what we are seeing in the picture, right? If this one here is -1, the -2 is a little bit to the left of it. Right around here is when I see a concavity change, is when I see a tangent line that wants to cross the function. Because visually, this is how I identify inflection points in curves. I look at the point where the tangent line wants to cross the function. And that coincides with the part of the function where it looks the most straight. It looks like a straight line over there. It's very little curved. So that's how you identify that it's almost straight. It's not curved because the curve is changing direction. It used to be up, and then it's going to on the other side be down. Okay, so question number 2 is going to be quite different from that. Consider a function with a domain from A to B. The following diagram shows the graph of f prime, the derivative. This is something that also happens quite often and we have to be careful with. Just because we're talking about a function f doesn't mean that what we're looking at is the function f. In this case, it was because he said so. But here we are talking about a function f, and we are looking at the graph of its derivative. So this type of question is really testing whether you know the concepts about this topic. It's nothing that you have to calculate. We don't even have an expression for the function, so there is nothing to calculate. All the questions that he's asking us are about find the value, but he doesn't mean a number. He means these letters that are all pointed out in the graph. So I'm going to put a copy of our little table here to remind us of all of the things that we know, keeping in mind that the one we are seeing in the graph is the middle line. It's f prime. So for part A, he wants f is increasing. F is increasing means f prime is positive. So we are looking for this part of the function here between the values of p and 0. I'll write down my answer, p less than x less than 0. And as for justify your answer, I'm going to say because f prime is positive. For part B, he wants the graph of f to have a local maximum. Well, f has a local maximum when f prime is 0, but f prime is 0 in a bunch of places here, p, 0, and t. As we've been discussing, not all zeros of f prime make a local maximum. Sometimes it's a local minimum, and sometimes it's a horizontal inflection point. But the 0 that we want for the maximum is the one that goes from a plus to a minus. And the only part in this graph that is going from a plus to a minus is here, x equals 0. Part CI wants f to have a local minimum, which is the opposite, right? It's a 0 going from minus to plus. So it's x equals p. That goes from minus to plus. And this time he asked us to justify, so you can say exactly that, because for x less than p, f prime is less than 0, and for x bigger than p, f prime is bigger than 0. And finally, for part C2, he wants f to have points of inflection. Points of inflection are when the concavity changes. So when f has points of inflection, here the concavity is changing from plus to minus or minus to plus, so f double prime would be equal to 0. But because the graph we are looking at is the graph of f prime, it's going to be better to look at the relationship between these things that says that the points of inflection of f are the turning points of f prime, both the maximum and the minimum. So we're talking about this point up here, which is q, this point here, which is r, and this point here, which is t. Now the question didn't ask us to do this next thing that I'm going to do, but if you want to understand better, we can go back to just the graph and sketch the graph of f based on the information that we have about f prime. So we can start, for example, with the fact that this is a local minimum. We don't know the value of f at that point, but I'm just going to put it anywhere. That's a local minimum, so it's looking like this. It has concavity up. And the next interesting point that we talked about was this one. A turning point of f prime is an inflection point of f. Concavity was up, so when it reaches here, it has to be concavity down. I'm going to put a tangent line at the inflection point in my picture. I always like to do that because it really highlights the fact that that is the inflection point, because the tangent line at the inflection point looks really specific. It's crossing the function. So I like to include that in my sketches. And here, the next interesting point that we're going to see is 0. 0 is a local maximum of f because it is this type of 0 in f prime going from plus to minus. So my function has to keep going up until 0. Then it's going to have a turning point. R is going to be an inflection point of f because it is a turning point of f prime. So I have to be a little more careful how I draw the function around here because you have to be able to see the concavity change. Down, and here I am going to change it to concavity up. I'm going to put a tangent line in the sketch for the same reasons that I was just saying, just to highlight the inflection point. And the next interesting point here is T. T is also an inflection point because it is also a local maximum of f prime. But at the same time, f prime is 0 here, okay? T is also an x-intercept of f prime. So this has to be both an inflection point and a stationary point. It's one of those horizontal inflection points, so I have to draw even more carefully because it needs to look horizontal. And let's put the tangent line over there. So yeah, this is the graph of f. And the other type of problem in which all of these concepts appear a lot are the kinematics problems. These two things are very closely related because, as we were mentioning before, every derivative is the rate of change of something. And in terms of kinematics, the something are the physical properties of a particle. So speed of the particle is the rate of change of position. If the position is changing slowly, that is a small speed. If the position is changing faster, that is a large speed. So f is going to be position, f prime is going to be speed, and the rate of change of f prime, so f double prime, what is the rate of change of speed? It's acceleration. We actually have to be kind of careful here because this vocabulary comes from physics. So speed is not actually what I need to say. I want to say velocity because velocity can be positive or negative. So there is one established direction, say moving to the right is positive. So a positive velocity goes that way, negative velocity particle goes this way, but the speed doesn't have a direction. The speed is just a number in absolute value. And this comes up in a lot of problems, okay? So pay attention to that when it comes up. So the problems are here. I'm going to put the problems up on the screen for a little bit in case you want to try them before I solve them. But I'm actually going to put the solutions to these problems in a separate video. Problem 4 has a graph here, and it asks a bunch of questions about that graph. Problem 5 is kind of similar. There's an expression for a function, there's a graph, and then a bunch of questions about the graph. And then this one will be the last problem on the list.